Bismillahirrahmanirrahim. Assalamu alaikum, dear students. Welcome to the online lecture on control systems, nonlinear control systems theory. And today we are going to discuss another special topic in this course, which is fault tolerant control systems. Fault tolerant control systems in this course will be a standalone topic, and we shall only be introducing the concepts and main ideas related to the fault tolerant control systems. And this lecture will serve only as an introduction to this type of control systems. If you are looking to become an expert, or if you are looking for an in-depth knowledge on fault tolerant control systems, then I recommend that you take a graduate level course on fault tolerant control systems, or also you can do self studies if you have basic concepts that can be provided by that are to be provided in this lecture. So like we discussed the adaptive control as a standalone topic, and similarly we are going to discuss fault tolerant control as a standalone topic, but it is an in-depth field of study, and you can also do research in fault tolerant control systems if you are interested. So first of all, I begin with the question that what is a fault? What is a fault with respect to control systems? Being control systems engineers or designers, we look at different systems in the form of maybe state space or transfer functions or differential equations. So if you are given an LTI system and you want to know with respect to this model of the system what is the meaning of the fault, so then there are three possible fault types that you can study. So if there is any fault in the system itself, that any fault that changes the dynamics of the system, then that fault will actually change the A matrix of the system. And if a fault occurs in the actuator, then B matrix will be affected by that fault. And if a fault occurs in the sensor, the function of the sensor is no longer available, or if the function is distorted due to an event, then the C matrix will be affected. So basically a fault is an event that could change either one or more of the A, B or C matrices in the LTI system. And similarly, if you look at nonlinear systems, x dot equal f of x plus g of x times u and y is equal to h of x, where f of x, g of x and h of x are nonlinear functions of the state variable state vector x, then fault is an event that causes changes in the nonlinear functions. So system fault will change f of x, actuator fault will change g of x, and sensor fault will change h of x. So this is what it means, what the fault really means in terms of control systems. So what is a fault tolerant control? So let's look at the block diagram of fault tolerant control systems. We have a plant that we want to control the output or the state vector of this plant, and for that we use some control input. Control input could be just the feedback control, or it could be a combination of feedback and feed forward control. So this is normal, but what is special about fault tolerant control is that we have some additional features. For example, we have this fault detection and diagnosis module, which basically works with the input and output information of the system, and it tries to detect any faults, and the fault information is provided to some sort of supervisory control. So these are some new blocks which are introduced due to the fault due to the fact that we are trying to incorporate the capability to tolerate faults in the system. So you have fault detection and diagnosis module, you have the supervisor or supervisory control logic, and sometimes you might also need human interference or interface. And then there is the feed forward or feedback control is not just the usual feed forward or feedback control, it is reconfigurable control. So the control could be reconfigured based on the occurrence of different faults in the system. So this is the pedagogy of fault tolerant control systems, and I just want to go in a little bit further discussion of fault detection and diagnosis and supervisory control and reconfiguration mechanisms. So multiple model in this lecture we are only going to discuss one type of fault tolerant controls. There are many types of fault tolerant control schemes and methods. We don't have time to go through all of them, but here is one method that is quite common and relatively easy to understand compared to the accuracy or the performance that it offers. So multiple model fault tolerant control approach is the approach where you anticipate possible faults that may occur in the system and then develop mathematical models for each corresponding fault situation. So in this case you have multiple models, as the name suggests. Each model correspond to different fault situations. For example, you have different A matrix, B matrix and C matrix for different fault situations. Design control law that corresponds to each fault situation. So this is all of this we are doing beforehand, before actually implementing or deploying the system. We are doing this all of this calculations and modeling and controller design, and then once we do that, then we develop a threshold based fault detection and diagnosis scheme. Well, fault detection and diagnosis scheme is usually threshold based, but there are many fault detection and diagnosis schemes available in the literature. You can also look at the schemes that have fixed threshold or adaptive threshold, or some sort of dynamic thresholds. Devise a switching law based on thresholds of fault diagnosis, and sometimes there might be different thresholds for the diagnosis or detection of fault, and there might be some other thresholds for the decision of reconfiguration. So sometimes a fault might be detected, but the reconfiguration decision may not be executed right away, or sometimes it may be executed right away, and sometimes you wait for some time, and maybe if the magnitude of the fault is not large enough, then you can actually wait for some time, and if the magnitude of the fault keeps on growing, then you execute the reconfiguration decision. Otherwise reconfiguration decision may be avoided. So I'm just discussing this for the sake of completion of the discussion. Improve the threshold values based on machine learning or adaptation rules. So this is also one of the perspectives, and there are many other perspectives. So this is a multiple model fault tolerant control. You anticipate possible faults that might occur, then you develop mathematical models for each of the fault situations, and then you design the control law corresponding to each fault situation, then the fault diagnosis method, then the switching laws or supervisory control, and then there might be machine learning or adaptation of the thresholds. Alright, so next we shall be looking at an example of multiple model fault tolerant control, and this example is concerning the fault tolerant control for a spacecraft. Spacecraft need fault tolerant control more than anything else for multiple reasons. First of all, because the space environment is very hostile, and there are charged particles in the space, and there are a lot of temperature difficulties and other unexpected variations due to which spacecraft could be experiencing more faults. The occurrences of faults are more frequent in spacecraft compared to the systems that operate within the atmosphere of the Earth. And also the other reason why fault tolerant control is more important for spacecraft is that spacecraft are not accessible for the humans to repair, and they do need the self repair capability or fault tolerance capability in order to have a longer life duration, because space missions do involve a lot of financial resources. So in order to save those resources or make the investment durable, it is highly desirable to incorporate fault tolerant control in spacecraft. So spacecraft model, there are multiple ways to model a spacecraft. A common model is to use the Quaternion vector. Quaternion vector is a vector of 4 variables which are called Quaternion variables, and the angular velocity of the spacecraft is in 3 dimensions. You can have a body fixed frame of reference, and with respect to body fixed frame of reference you can measure the angular velocities of the spacecraft in 3 dimensions. So consequently the angular velocity vector has 3 components: omega 1, omega 2, omega 3, and the Quaternion has 4 components: q1, q2, q3, q4, and then the 3 of the components are denoted by this variable q, which is not bold compared to the full Quaternion, and q4 is represented separately. Alright, so with respect to Quaternion, the equations that represent the kinematics of the spacecraft are represented as follows. Q dot, which is a vector with 3 variables, it is equal to 1/2 q4 omega minus omega cross q. So this is the cross product between the 2 vectors, omega and q, and this is q4 is a scalar and omega is still a vector, and q is also a vector of 3 variables. So this is the 3 of the Quaternions, the dynamics of the 3 of the Quaternion variables. You can find out more about Quaternions and what they represent in terms of the orientation of, basically Quaternions are used to represent the orientation of the spacecraft. Sometimes people use Euler angles, roll, pitch and yaw angles. Especially in aircraft you can use roll, pitch and yaw angles. Sometimes people use rotation matrices to represent the orientation of different rigid bodies, and Quaternions are also very effective way of representing the orientation of the spacecraft. So rate of change of orientation, the dynamics related to the orientation of the spacecraft, those are kinematics of the spacecraft. q4 dot is 1/2 into dot product between omega and the Quaternion vector. This is the dot product omega transpose q, and that will give a scalar quantity which will be the q for the derivative of the 4th Quaternion variable. Then there are dynamics of the spacecraft. Dynamics of the spacecrafts are usually related to the angular acceleration and the torque applied to the spacecraft. So torque can usually applied in 3 dimensions: u1, u2, u3, and correspondingly there could be angular acceleration in 3 dimensions. So omega 1 dot, which is the angular acceleration in say x-axis, you can call this angular acceleration along y-axis and angular acceleration along z-axis, and those axes are usually correspond to the body fixed frame, but we are not going into much detail of that. You can consult any standard textbook on space vehicle dynamics and control, and you will see how this model is derived and the detailed implications of this model. Right now we are just looking into we treat this model as given to us, and J1, J2, J3 are the inertia values. We assume that the spacecraft is symmetric in nature, symmetric in shape. So the inertia matrix is a diagonal matrix where we have J1, J2, J3, which are the diagonal elements of the matrix. J1 would be the inertia about the x-axis, and then this is the inertia about the y-axis, and this is the inertia about the z-axis. Alright, so these are the equations, the kinematics and dynamics of the spacecraft. Once you have the kinematics and dynamics, you can design the control law for the spacecraft. This is nonlinear control. You can see here that this k gain is nonlinear with respect to the fourth element of the quaternion. Otherwise, mostly it is linear with respect to angular velocity variables. And also I want to point out that there are 7 variables in this model. So if you call it like a state variable model or state space, this is basically the state space model. And in this state space model you have 7 states. 4 of the states are quaternions, and the next 3 states are angular velocities, and these are the dynamics of the states. So, and then the control is basically a vector which has 3 components. This u is a vector with 3 components, u1, u2, u3, and u is equal to minus k times quaternion vector, this one, and minus c times omega, which is this vector. C and k are constant gains. Actually k is not a constant gain, k depends upon the value of q4, and also this small k is a positive constant, c1, c2, c3. So this c is a diagonal matrix which with the diagonal entries c1, c2, c3, which are positive constants, and this is multiplied with the inertia matrix J, which is also a diagonal matrix with the elements J1, J2, J3. So these are the values of C and K. We shall not be discussing how this control law is designed. Once again, if you are interested in the spacecraft dynamics and control, this in itself is in many universities, spacecraft dynamics and control is offered as a graduate level course for the control systems students or aerospace students. So this is our control law. J is the inertia matrix, which is a diagonal matrix, and U is the control vector, which has 3 elements, U1, U2, U3. So this is the state space model with feedback control, and you can see that this is the full state feedback. It has the quaternion vector with 3 quaternion variables and the 4th quaternion variable and 3 variables of the angular velocity. So this is full state feedback control. And in order to implement this control, of course, you need to measure all of the 7 states of the spacecraft. Right, so next we look at a list of faults corresponding to multiple models. Okay, let us consider the following faults for our spacecraft. First fault number 1 is partial failure in actuator corresponding to U1. So let me briefly tell you what kind of actuators are used in the spacecraft. Usually there are 2 main types. One is the thruster pair. The thrusters could be ion thrusters or jet propulsion thrusters, and those thrusters are used in pairs and they are mounted across 3 axes. And in order to control the spacecraft in 3 axes, in order to control the orientation of the spacecraft in 3 axes, you need at least 6 thrusters or 3 thruster pairs. And then another way to control the orientation of spacecraft is to use the momentum wheels or reaction wheels. Momentum wheels or reaction wheels operate on the law of exchange of momentum, and once you change the rotational velocity of the momentum wheel, uh, in order to conserve the momentum of the overall system, the spacecraft tends to rotate in the opposite direction. That is opposite to the rate of change of angular velocity of the reaction wheel or the momentum wheel. Okay. Fault 2 is the partial failure of actuator corresponding to U2, and fault 3 could be partial failure of actuator corresponding to U3. So these three faults might be, you can say that these are the faults that might occur in the thrusters of the spacecraft, or maybe the faults that might occur in the reaction wheel or momentum wheels of the spacecraft. Then fault 4 could be the failure of the sensor that is measuring omega 1. That could be a gyroscope or maybe an IMU. Failure of the sensor measuring omega 2 and failure of the sensor measuring omega 3. I'm just presenting these faults as an example. We are not doing a professional project on spacecraft. We are just trying to understand how a multiple model fault tolerant control could be implemented on a practical system such as spacecraft. So this is all for the sake of concepts. And so if we consider these 6 faults, so as a result we should have 7 dynamical models, including the normal model. So one model shall correspond to the normal behavior of the spacecraft where no fault has occurred, and 6 models shall correspond to 6 different faults that might occur in the spacecraft. You might have noticed that we are considering one fault at a time. If you were to consider simultaneous faults, then number of models will increase as the Cartesian product, the magnitude of the Cartesian product of the different elements of the faults. So that will become a big set of faults if you were to consider any of these faults to be occurring simultaneously. Okay, models corresponding to each fault. For partial actuator failure, for example, we can have a multiplication factor of 0.5 applied to the control signal input, and for sensor failure the output of the sensor shall be 0 for all time. So we have to model how the actuator fails. We can also multiply the actuator failure, we can also represent the actuator failure as a total failure, and we can also represent the actuator failure as a partial failure. So 0.5% failure means that the actuator loses 50% of its power or thrust capability, and 0 here means that the sensor is fully dysfunctional after the fault. So when the sensor is dysfunctional, then based on the observability property of the system, in this case the 3 faults that we have considered, even after the occurrence of these faults the system does remain observable, of course, because this example is pre-calculated and it's been prepared for this lecture. That is why I have considered only the faults that do not affect controllability and observability. In practice, when a fault occurs, you have to do post-fault controllability and observability analysis. If you lose controllability after a fault, then you might have to switch to redundant equipment in the system, or if there is no redundant equipment, then post-fault capability control capabilities may not be as much as the control capability before the occurrence of the fault. Similarly, if the system does not remain observable after the failure of a sensor, then full state feedback might not be as effective as it were before the failure of the sensor, and sometimes it might not even be possible to control some particular states of the system because you don't know what their values are. And I just repeat the model of the spacecraft that we just discussed, but I just want to point out that if an actuator fails, then this U3 might become 0.5 into U3. So this will be the change in the model that will be representing the actuator failure, and similarly the change in the model that will represent the sensor failure would be that instead of using the omega as a feedback in the feedback control law, we might be using the estimate of omega that might be coming from the state estimator, such as extended Kalman filter or any other nonlinear observer that you can use for this system. So if the sensor fails, then the observer will come into play, and then the feedback control law will no longer be based on the full state feedback. It will become a dynamic compensator. Okay, similarly, when this fault occurs, the post-fault gains of the controller may not be the same as pre-fault gains. You might be changing the gains after the occurrence of faults, or if the fault is too small, maybe after the fault this becomes 0.98 U3, only 2% of the actuation capability is lost, then maybe you will not be willing to change the gains of the control. So it all depends on the magnitude of the fault in practical situations. We are just looking at this example in order to clarify our concepts related to fault tolerant control and its implementation, and how multiple models are developed for different faults in actuators and sensors. Alright, and also although we have not included system faults here, but some faults may change the inertia matrix values for the spacecraft. So if those change, then those can also be modeled in terms of change in J1, J2, J3 in the model. So next we have to look at, after developing multiple models, we have to look at fault detection and diagnosis. In this case we shall be looking at the fault detection and diagnosis, where we compare the predicted state vector value by each of the 7 models with the actual state vector value. So this means that we are actually simulating the state trajectories corresponding to different fault models, and we are comparing those predicted state trajectories with the actual state trajectory and trying to match the trajectory with the trajectory predicted by different models. Okay, so in this case we use a 3-level fault detection and diagnosis. On level 1, we compare the state variables. These are the xij is the state variable due to, so I is the index corresponding to different models. So in this case we have 7 models, 6 corresponding to different faults, and a normal model which has index 0. And we have 7 state variables. So J is the index of state variables, which are 4 quaternions and 3 angular velocity variables. So xij is the ith state of jth model, and we compare this with the state of nth model. Here you can say that we actually compare the states with the actual states. So I don't know that there is some confusion here, but we compare the jth state. Yes, we compare the jth state of ith model with jth state of actual measurement, that we have taken. I should not have used the subscript n here, because n I have used here for number of anticipated faults, but n means that this basically this is the state variable value for that we have calculated. This is the actual state variable value, and this is the state variable value that is predicted by ith's model. So we calculate Eij for all possible state variables and all possible models. And we know, for example, let us suppose there are like 4 quaternions and 3 angular velocity variables. So model 0 predicts quaternion values to be some certain numbers, and actual measurement give us some other numbers. We compare the number corresponding to number of q1, like for example value of q1 predicted by normal model with the value of q1 actually obtained from the sensors, and then if those values are same, then the error will be 0. If those values are different, then error will have some non-zero value. And then we will have, for each of the model, we will have error value for each of the 7 state variables. So this will be the state variable level error. Then we will be using this level, this error on the state variable level into the next next hierarchical level of fault detection, which is fault rejection number. So fault rejection number is Nij for each fault case I. So now okay, and each state variable j, fault rejection number is 1 if the residual for from the so this is the residual. This error can be considered as a residual value or error value. You can use any term for it. So here the residual term means this error from the first level. So this is the first level of calculation, crosses a threshold h. So if this residual, if this difference crosses a threshold h, then this whole thing will become 1. It will be close to 1, and 1 minus 1 will be 0. So fault rejection number will be 0 if the threshold is crossed. If the threshold is not crossed, then the fault rejection number will be 1. So fault rejection number having value 1 means that there is no possibility of fault, and fault rejection number equals 0 means that there is a possibility of fault. So if there are and on the other hand, you can also say that if fault rejection number for some model is 1, then that means that that model is basically the actual if the fault rejection is 1, then for that model the errors would be 0, and that model will be actually very close to the sensed values. Alright, so next, the third level is fault hypothesis. Fault hypothesis is generated if fault rejection number for a particular fault is less than a second threshold V, which varies between 0.9, 1.9, 2.9 and up to so on, m minus 0.1, where m is the number of states, and 7 in our case study. In this example we have 7 states in the spacecraft model, so it can go from 0.9 up to so on. 7 it would go to up to 6 or 7.9. 7 minus 0.1, which will be 6.9. Sorry, this will go to 6.9, from 0.9 to 6.9. And V depicts how many states are in agreement with the given nominal model. So if there are more states that are in agreement with the given nominal model, then it means that that model is the one which is active, and so our hypothesis will be true if if this nij is 1 and this is let's say 0.9, then you have 0.1 here, and then this hypothesis will be strong. Otherwise, if this is 0, then this hypothesis will be weak. Okay, so fault hypothesis depends upon the fault rejection number, and fault rejection number depends upon the difference between the state variable values and the actual state values. So in this case, this is one of the methods of fault detection and diagnosis. You can also use there are many other methods. So this just give you some concept about fault detection and diagnosis. Okay, then there is reconfiguration, and as soon as the fault identity is diagnosed, which means that as soon as you have diagnosed which model is actually active for the currently in the system, then the corresponding control law can be activated, and for that you can use multiplexer or any switching any type of switching which selects between any of these models to be the currently active model, and on the basis of that you can reconfigure the control. So control will be there is control law corresponding to each of these models, and which control law is active at what situation will be dependent upon the switching criteria. Alright, so next we look at some of the results, and here are the results from one of the research papers for which I will provide reference. The research paper has used same dynamical equations of the spacecraft and control law and the same scenarios, but it has some more in-depth discussions that we have avoided in this lecture, because we want to focus on the concepts rather than going into the details of. Alright, so you can see here that there are three types of curves here, a red curve, a blue curve and a green curve. And you can see that blue curve is the normal model or normal trajectory of the spacecraft, red curve is the faulty trajectory, and the green curve is the reconfigured trajectory, where reconfiguration decision has been taken at t is equal to 5 seconds. So round about somewhere in the very beginning of these graphs. So fault occurred in the very beginning after maybe 3 or 4 seconds, and within 1 or 2 seconds of the occurrence of fault, the reconfiguration was carried out, and these trajectories depict that without fault the behavior of the spacecraft would have been as shown in the blue curve. So these are the 7 state variables: q1, q2, q3, q4. These are the values of the quaternions, and omega 1, omega 2, omega 3, these are the values of the angular velocities of the spacecraft. And you can see that if no fault occurs, then spacecraft is actually carrying out an orientation maneuver, where it is trying to change its orientation and trying to maybe it could be to take pictures of an object in space, or maybe it could be change in orientation in order to transmit data onto the ground station, whatever reason. But spacecraft is in the middle of the slew maneuver or orientation change maneuver, and some fault occurs in the actuator. If you reconfigure for the fault, then you get the green trajectories, which are very closely which are very close and asymptotic to the blue trajectory, which means that after reconfiguration for the fault, post fault performance is quite acceptable. And red trajectories indicate that if you do not have fault tolerant control in the spacecraft, then the spacecraft will follow the red trajectory. So this basically motivates the fault tolerant control and shows the importance of fault tolerant control, that instead of losing the spacecraft orientation altogether, you can be able to achieve your goal of slew maneuver with 100% accuracy in this case, due to the availability of fault tolerant control on board the spacecraft. And that is the reference paper from where I have taken most of the equations and methods that are discussed in our case study. This is actually one of my initial work on my PhD at the University of Michigan. I wouldn't say it is one of the best papers in fault tolerant control systems theory, but it does give you some insight into fault tolerance for spacecraft attitude management. And that is it for today's lecture. And in the end, I would just recap in a couple of minutes what we have discussed in today's lecture. So in today's lecture we have discussed fault tolerant control, and we have looked at one example related to spacecraft control. So what is a fault tolerant control with respect to, what is a fault with respect to control systems? It is a change in A, B or C matrices, or f of x, g of x, h of x functions in nonlinear systems. And then we looked at the block diagram of fault tolerant control, where we see some additional features corresponding to the block diagram of usual control systems or classical control system. We have a new block of fault detection and diagnosis. We have new block of supervisory or switching control, and the old blocks of feedback and feed forward control are changed as well into reconfigurable feedback and reconfigurable feed forward control. And then we looked at multiple model fault tolerant control approach, which is based on some steps which involve anticipation of possible faults, development of mathematical models corresponding to faults, development of and design of control law corresponding to different faults, and development of threshold based fault detection and diagnosis scheme, development of switching scheme, and then there might be some involvement of improvement of thresholds that we have not discussed in this lecture, but it's worth mentioning here. Then we looked at the example of fault tolerant control for a spacecraft which has 7 state variables and a control law that is non-linear, but it's mostly linear except for this non-linear term. And then we looked at 6 different fault scenarios, 3 actuator faults and 3 sensor faults. And then we looked at how the dynamical model of the spacecraft would change in response to different faults that we consider in this lecture. So here there will be change in the multiplication factor with control input variable, and here we shall be using the estimates of the states instead of the state feedback when the sensor failure occurs. Fault detection and diagnosis, we discussed this scheme of 3-level scheme of fault detection and diagnosis, which involve residual generation, fault rejection number generation, and fault hypothesis generation. And in the end, from the fault hypothesis we decide whether certain fault has occurred or not. Then we discuss the reconfiguration, which is very simple. You just have to select one of the models based on the information from the fault detection and diagnosis. Then we looked at some results which would help us get motivated about the fault tolerant control. You see that if we have the fault tolerant capability, then we are able to achieve our goal with some deviations. You know, this green lines are deviated from the blue lines only because of the delay in fault detection and reconfiguration. After the reconfiguration is done, we go back to the desirable actual performances. And if we do not have fault tolerant control, then this is the depiction of the results without any reconfiguration and with fault occurring in the spacecraft. And there is a reference, and that is it for today. I hope that this lecture was understandable and useful for you, and if you have any questions, please let me know. Thank you for listening.